welcome back to 6th grade science. So in the last video we started talking about forces part 1, and today we're going to finish up with forces part 2. So we got talking about different forces, friction, all of that stuff. In the beginning of the last video I mentioned different fundamental forces of the universe, and one of them was gravity. So to start today we are going to talk about gravity. By definition, gravity is a force between two things that have mass. Specifically, it's a force of attraction between those things with mass. Now, anything can have mass, no matter how big it is or how small it is. So, I have mass, you have mass. The camera that I'm recording this on has mass, my phone has mass, this wall holding the building up has mass. Most things in the universe have mass. So, well, because they have mass, they exert gravity on each other. Most of the time that sense of gravity is not necessarily noticed. Like, I'm not suddenly sucked into this wall because it has more gravity than me. Reason being is the Earth is so big and so strong as far as the force of gravity, it kind of makes this one irrelevant. Just like things that are flying in the sky, gravity is still affecting them as far as gravity from the Earth. Gravity itself acts on things that don't have to be touching. So, for instance, when you jump in the air, you're pulled back down to Earth because of the gravity. At one point in time, I wasn't touching the ground, but gravity still pulled me down. The bigger the item is, the longer that this space can go that it has an effect. The sun, which we'll talk about a little bit later, still has a massive amount of effect on Earth because of the size of the sun and its gravity. So if we were a lot closer to the sun, then that gravity would be a lot stronger than it is now. Planets that are farther out, like Jupiter or Neptune, just to name some off the top of my head, those planets are affected a lot less by the gravity of the sun than we are. They're still affected by it, but it's not as strong as ours is. The greater the amount of mass, the greater amount of gravity an item has. I kind of alluded to this a little bit, but Earth has gravity. This gravity is constantly pulling you towards the center of the Earth. Just like when I jumped, it pulled me back down. It also pulls items from the sky back down. So this could be meteors that are coming in from outer space, or it could be someone jumping out of a plane for fun, aka a skydiver. Besides pulling things down, Earth's gravity is also important with keeping satellites floating around the Earth. Now, when I say the term satellite, the first thing that comes to your mind is probably one of these, which technically is correct, but that's an artificial satellite. There are other types of satellites. Essentially, the Earth is a satellite around the sun. Another naturally occurring one that we have is the moon. So the moon is considered a satellite around Earth because it goes around Earth due to Earth's gravity. Fun fact, there's two satellites that are actually chasing each other around Earth, and they are used to measure gravity. Gravity in general is what keeps the Earth and other planets revolving around the sun, which I know I said, but sometimes I like to repeat myself because it helps get through to you guys. Now, I can't talk about gravity without talking about weight. What is weight? Is it how many pounds a person weighs? Not really. Weight measures the force of gravity pulling down on an object. So the more mass an item has, the heavier weight it will be because gravity has a bigger effect on it. Just like with force or other forces in general, the SI unit for weight is the Newton. So on Earth, approximately 1 kilogram is equal to about 10 newtons. On the moon, however, 1 kilogram would be worth less than 10 newtons. But why? This is why weight doesn't really make a lot of sense as a measurement. So you have something that weighs 750 pounds on Earth. On the moon, it's going to weigh a lot less. And the reason is gravity is weaker on the moon, so it's not pulling down as hard or as much on the object. Depending on the planet you're on, your weight of a certain mass is going to be more than Earth's or less than Earth's. It just really varies depending on gravity. How do we measure weight? Well, if you've been to the doctor's office recently to get your physical, you probably stepped on a scale. And that's what we use to measure weight, is a scale. And what's a scale measuring? The force with which gravity pulls an object downward. Gravity is probably a term that you've heard of before. And if I asked, who comes to mind when you think of gravity? Would any of you say Newton? Specifically Isaac Newton? It's a story that you might be a little familiar with, but One day, Isaac Newton was sitting under an apple tree and an apple fell and hit him on the head. And that's how gravity was discovered. Except not really. It's a nice story, the idea is there, but it didn't really happen like that. Before Isaac Newton even existed, people knew about what gravity was. The story does make a nice way to remember it though. So why am I talking about Newton if that story's not true? Newton came up with the law of universal gravitation. What's that? Newton's law of universal gravitation is that the force of gravity affects everything with mass in the universe. The force from the apple in the story that hit Isaac Newton in the head, supposedly, is the same force that holds the moon rotating around Earth, or Earth rotating around the sun. Going along with this law, Newton says that the strength of gravity is dependent on two factors. And we've already kind of talked about them. The first one is the mass of the object. The greater the mass, the greater gravity. Or the less mass, the less gravity. And the second is the distance between two objects. The closer together an object is, the more gravity there is. The farther away an object is, the less gravity there is. I told you the story about Isaac Newton and the apple, and then I told you it wasn't true. Well, I'm gonna follow suit with that. So Newton's law of universal gravitation is kinda true, but it doesn't account for everything. Mr. Morgan, why would you tell us that if it's not true? Well, like I said, it doesn't cover everything. It can predict the motion of most objects due to gravity, but it doesn't predict all of them. Basically, it doesn't describe gravity, it just describes its effects on objects. So in the 1900s, along came Einstein. Now, you probably are pretty familiar with Einstein. He looks like this. Or should I say, he looks like this. Einstein ended up developing a theory that explains the parts of Newton's law that the law didn't explain. So what does Einstein say it is? Well, instead of gravity being a force of attraction between objects that have mass, Einstein says it's a result of warping space-time instead. Space-time? What? That was the 1900s, and it was just a theory. At this point, it's still technically a theory. Specifically, it's called Einstein's theory of gravity, but it's supported by a bunch of evidence that we've discovered since he came up with this theory. And it's the most widely accepted theory that we have in relation to gravity. In the PowerPoint, you guys are gonna watch a video, and in that video, it talks about why this theory works and why it makes sense. And I just want to note that it's going to talk about black holes and how we couldn't really prove some of the existence about black holes. Fun fact, about a year or so after the video was created, we actually, and by we I mean scientists, were actually able to photograph a black hole, which might not seem like a big deal, but it totally is. But let's get back to gravity. So I keep talking about gravity pulling things down towards the center of the Earth. And if you've ever seen someone skydiving, then you know that they pick up speed as they fall. Or if you've dropped an object, you understand that it accelerates. When an object is falling to the ground, gravity causes it to accelerate. The longer the object falls, the higher the velocity gets. Whoa, Mr. Morgan, you just said acceleration and velocity, and I thought they were different things, and what's happening right now? Remember that acceleration is meters per second squared. Velocity is meters per second. Remember too that acceleration is the rate of change of velocity over time. So that's how they're connected. Velocity increases by 9.8 meters per second squared. Hold up, I just said that the SI units for velocity were meters per second and acceleration was 9.8 meters per second squared. Nope. Hold up, I just said that the unit for velocity was meters per second, and now I just said meters per second squared. I'm talking about velocity in its sense of acceleration. So it's accelerating by 9.8 meters per second squared. What does that mean? Well, after falling for 1 second, the velocity increases by 9.8 meters per second. After falling for 2 seconds, the velocity increases by 19.6 meters per second. And it continues like that for each second. So we have our blank number of seconds, and then we have our meters per second. So together, that's where you get the meters per second squared, which remember is acceleration. If this item continued to fall for 30 seconds, its acceleration would be 294 meters per second. So velocity increases by 9.8 meters per second squared. How much does acceleration increase by? Well, acceleration doesn't increase. Gravity acceleration remains the same, for the most part. And gravity acceleration is 9.8 meters per second squared, which is tied into the velocity component I discussed earlier. All objects are going to accelerate at the same rate from gravity, and that's your 9.8 meters per second squared. Doesn't matter how heavy an item is, how much mass there is, it's going to accelerate at the same rate. If you don't believe me, watch the video in the PowerPoint that follows up from this. Now, I just said that it's always at the same rate, but there are outside factors that can affect this. And one such outside factor is air resistance. If you have a bunch of air resistance, then your acceleration and your velocity is going to vary. But in a theoretical world where that doesn't exist, it's going to remain 9.8 meters per second squared as a constant for gravity acceleration. We're currently discussing overall forces, part 2. Last video, forces, part 1, so we talked about forces. Now I want to talk about projectile motion. You'll see how they connect in a minute. Projectile motion is the movement of an object in a curved path towards the ground. Where does the curvature come from? This is where forces come into play. The curvature is due to a horizontal force, as well as the downward force of gravity on the object. So if you didn't have gravity, the item could continue in a perfectly straight horizontal path, or in whichever direction you sent it. But because you have the horizontal path, a horizontal force going this way, and you have gravity pulling down, it's going to curve from its original position. Really good examples of this are both cannonballs and arrows. Last up for today, orbital motion. Well, if you had to guess, orbital motion's probably talking about the planets, kinda, because the planets are in orbit. So what do I mean? So orbital motion technically doesn't just refer to planets. It is any time that an object is moving forward, but also having gravity pull on it. And remember, for gravity to be pulling on it, it has to be being pulled towards another object, whatever has a stronger gravity. The forward velocity of the object combines with the acceleration of the gravity towards another object. The result of this is a circular or an oval-shaped path. And essentially one object just continues moving around the other until something comes in and causes that to change, like a giant meteor, for example. The reason that the Earth orbits the sun is because the sun has much stronger gravity than the Earth. That's why all of the planets in our local solar system rotate, they orbit around the sun. How come the moon doesn't orbit the sun? The sun's gravity is stronger than the Earth's. The reason being is that the moon is in such close proximity to the Earth, the gravity that Earth is putting on the moon supersedes that of the gravity the sun is putting on the moon. That's everything I have for you. We are finished with Forces Part 2, and after the PowerPoint after this, next up we are going to spend some more time talking about good old Newton. As always, if you have any questions, please reach out to your teacher, whether that's Miss Cameron or myself. Bye!